In this video, we will start looking at confidence intervals. The idea behind a confidence interval is that we take our sample data, we calculate our sample statistic, such as a proportion, which is the first type of confidence interval we look at, and then we want to make an estimate about the population proportion. So we take our sample proportion and we now give a range of likely values for our population proportion. So we kind of build it around our sample proportion. Our starting point is our sample proportion, which we also call our point estimate. So if you take a sample and let's say 40% of the students in your sample own a car, you would say, hey, my best guess for all the students at Mesa College would be that 40% of the students own a car based on my sample proportion I got. So this is what we call a point estimate. It's one number, a single number that is based on our sample data that we can use to represent our population data. So that's going to be our starting point. Then we add and subtract a margin of error to it in order to find the upper and the lower value of our confidence interval. So just to look at an example over here, we are looking at 53% of the sample who were opposed to Prop 19 with a margin of 3.5. And then it says later on it was defeated with a 54% no vote. So our parameter over here is our population value. That's the 0.54 that voted no. Our statistic was the 53% in the sample that voted no, and that was 0.53. Now, using the margin of error over here of 3.5%, we would come up with a confidence interval of 0.53 plus or minus 0.035. And oftentimes we write it in interval format. So 0.53 minus 0.035 is 0.495, and then 0.53 plus 0.035 is 0.565. So we're pretty confident after taking the sample that the true proportion is between 49.5% and 56.5%. So our confidence interval is actually a range of likely values. And we're going to have, when we calculate this, we have a confidence level that tells us how confident we are of actually capturing our population proportion. The most common confidence levels are 90%, 95%, and 99%. So we can either be 90% certain, 95%, or 99% certain, but we can certainly use other values as well. So in StatCrunch, under the applets, we have a confidence interval section over here for a proportion. We're going to look at a proportion of 0.5. We'll look at an initial sample size of size 30, and let's just start with a confidence level of 0.95. 0.95 is really the most common confidence level. If I don't give you a confidence level, that's the one you would consider. In fact, we even looked at, remember, going back to the 68, 95, 99.7 rule, we said that 95% of our data is within 2 standard deviations. And if there's no confidence level given, that's actually the one we would want to use, because we would say, hey, anything within 2 standard deviations would be usual, where anything outside 2 standard deviations would be unusual. So let's compute over here our confidence intervals. And so we have 100 different confidence intervals. You can see that there's a black line at 0.5, which is actually the population proportion. Every time we take a sample of size 30 from this population, we calculate our sample proportion. For example, in this example, in this first line, our sample proportion was 0.6. In the second line, our sample proportion was 0.367, and so on. So you can see kind of that green dot in the middle of our line. That is the sample proportion. Around that, we would build our confidence interval. And then we go about 2 standard deviations to the right and 2 standard deviations to the left, and it gives us that green line. A couple things to notice over here. First of all, most of the lines are green, but there's a couple red lines. We would expect about 95 green lines and 5 red lines because we're 95% confident. Over here we're pretty close. We have 3 red lines, we have 97 green lines. So what that means, whenever we have a green line, that means we actually capture the population parameters. So our population parameter is actually included in the confidence interval. Where the red lines do not capture the population parameter, they do not touch that line of 0.5. So when you're taking one sample and you're building your confidence interval, you're not actually going to know whether you captured the population parameter or not. You don't know if it's one of the green intervals or one of the red intervals. So that's why we don't want to talk about probability in confidence intervals. We want to just say with, we are 95% confident that our confidence interval actually captured the population parameter. Another thing I want you to pay attention to is what happens when I change my confidence level. So let's say I change this to 80%. So if instead of 95%, I want to capture 80% of the data. And you can see that 2 things happen. My confidence intervals get smaller. You can see the lines are much, much smaller. And the number of red lines increases because in 80% confidence interval, I expect about 80 green lines and 20 red lines. Over here I had 76, so again that's pretty close. This time I have more red lines, a little more red lines than expected. But definitely you can see when I decrease my confidence level, I capture less of the data, and therefore my lines are smaller, my confidence interval is more narrow, but I also have more red lines. So how do we calculate the margin of error? Well, our margin of error is a combination of our z star, which is a critical value, and the second part is our standard error. This looks very familiar because it's very similar to the standard deviation of our sampling distribution for the sample proportion. The only difference over here is because I don't know the population proportion, I'm going to estimate it with the sample proportion. So instead of a p, you see a p hat there underneath the square root and a q hat instead of a q. So basically we have a standard error which estimates our standard deviation, and we have a critical value which is a value that separates likely from unlikely values. Those values are typically numbers that are close to 2. So let's look at an example how to find a critical value. So let's say we want to find a critical value for an 80% confidence interval. So the critical value is it's the positive value that separates the middle 80% from, the bottom and top 10% each, right? So I can go over to StatCrunch, I can look at the in-between curve, look at a standard normal curve because a z-star is a z-score, and look at this positive value that basically separates the middle 80% from the bottom and top. So we'll look at the between curve. We're going to change it to 80% in the middle. And this gives us the 2 z-scores, the negative 1.28 and the positive 1.28. Well, for the critical value over here for that calculation, we're going to use the positive value of 1.28. So our critical value for 80% confidence level is 1.28. And this is how you would do it every time. If I want to find the the critical value for 95% confidence interval, this would give us 1.96. By the way, this is where a z-score of 2 and -2 comes from, because it's just a 1.96 rounded up. So this is why 95% of our data is between -2 and +2, like we did in the empirical rule. Now we're going to use a little more exact values, so we would actually use a z-score of 1.96 instead. And real quick, our assumptions on conditions are very similar to before. We still need independence. We still need a simple random sample. We still need the 10% rule, which goes in hand with the independent. And the last thing is our rule of thumb, which has changed slightly because we don't know the population proportion. So now we want n times p hat, which is n times our sample proportion, to be at least 10, and n times q hat at least to be 10. So similar to before.